Kia ora Year 12, hope you're having nice holidays. Just wanted to make sure everyone understands that this video is optional and it's a proof of the result that we're going to use in chapter 9b of the textbook. And this result is a really cool one when we have two Poisson random variables. So if we've got a Poisson random variable x with parameter lambda and another one y with parameter mu, then we can just add those together. So if they're independent, then we can say that the distribution of x plus y is also a Poisson distribution, and it's going to have parameter of lambda plus mu. Now, when you use this, it kind of feels obvious, but I wanted to go through exactly where that result comes from. So this proof is going to involve quite a bit of sigma notation and quite a lot of manipulation. It's not too hard, but it's also not the kind of thing you're ever going to be asked to do in test conditions. So let's just go over what it means if we've got a Poisson distribution, and we'll work with x first. So the probability that x is equal to a particular value is e to the negative lambda times lambda to the power of x over x factorial. And the probability that y is equal to some particular value will be e to the negative mu times mu to the x over y factorial. Okay, so what I'm going to prove now is I'm going to work with a case where we've got x plus y and they're equal to some number, and I'll call that number k. And we want to figure out what that is. And if this result is true, then we're going to end up with this. E to the negative lambda plus mu to the power of lambda plus mu to the power of k over k factorial. So as usual, always keep one eye on where you're trying to get to, even though it'll seem quite far away for a fair bit of this proof. Okay, so this is where we want to end up. But what we're going to start with is to say, well, what does it mean to have the sum of two variables add up to give me k, a constant, right? For example, k might be 4. So the probability that x plus y is equal to k is equal to all of the ways that we can combine the x and the y to add up to k. Right? So that would mean getting x plus y is equal to k, and x is equal to all of the numbers up to k. For example, if k were 4, then we'd have to look at these cases. We'd have x is equal to 0, y is 4, and then x equal to 1, y is 3, and so on. So that's what this notation here is doing. It's saying let's slowly click over. Imagine this is your clicker, and you're starting with x equals 0. So you're saying, well, if x is equal to 0, what's the probability that the two things add up to k? And we keep going until we get up to k. So we can write that out like this. We know that the two random variables are independent, but we're not going to use that fact quite yet. So if x is equal to I, then y has to be the leftover, right? So here, if x is 0, y has to be 4 take away 0. If x is 1, y has to be 4 take away 1. So this is the same as saying y has to equal k minus I, and x has to equal I. And now we're going to use the independence assumption to say that we can split the two probabilities up and multiply them together, right? So that goes back to what we learned in AS about independent probabilities. So that step should feel pretty easy because we're assuming, way back at the start, we're assuming independence. If we haven't got independence, we can't do any of this. Now, the next thing to do is just to apply the definition using my basic Poisson definition. So for y is the variable with mu. It's going to be e to the negative mu times mu to the power of k minus I over k minus I factorial. And then for x, it'll be e to the negative lambda times lambda to the I over I factorial. Now, all I've done in that line is I've just applied my basic definition of a Poisson random variable from back in chapter 9a. Okay, so I'm just using basically this one here on x and y. I can do a little bit of simplifying here, especially if I look at where I'm trying to get to. Right? Remember, we're trying to end up with one Poisson random variable. I'm going to take this, and I'm going to chuck those together. That'll give me e to the negative mu minus lambda. And that's all I'll do in that line, I think. And that should be an I there. So mu to the k. Oh no, I'm going to split this up as well, right? So mu to the k, mu to the negative I, lambda to the I, divided by k minus I factorial times I factorial. The thing to do from here is to say, is there anything in there that hasn't got i's or k's in it? And there is, right? So this term here, we can pull out the front. So that's e to the negative mu plus lambda times the sum. So working through all of my cases, we've got mu to the k, mu to the negative I, lambda to the I. Now, I'm not actually sure why I split that up. That was a bit stupid. I'm going to unsplit that. I was just thinking that that doesn't add anything. Right, so we've got that. And then with these factorials, we've got I factorial and we've got k minus I factorial. But let's look at what we're trying to get to. Let's go back to the very first line and see where we want to be. All right, so in here, we've got this figured out here. Oh, that's not very good, is it? Let's delete that. Too many colors of pen. Sorry, guys. Okay. Oh, now it's gone away completely. Right, here we are. We've got negative mu plus lambda in here. We want to generate a k factorial here. Not really obvious how we should do that, but we can do what we often do in scholarship calculus, and we can force this in to the bottom line, and we can also chuck it into the top line. And looking at this, maybe this is going to come out of my sigma notation thing, right? Because I could do some kind of binomial expansion on this. So we're going to keep both of those thoughts in the back of our minds now. So we're going to multiply in k factorial here over k factorial here, I factorial, and k minus I factorial here, and mu to the k minus I times this. Okay, now the k factorial here is what I want to end up with in the end. And this is a constant, right? This is not depending on I, so I'm going to pull it through here. And that leaves me inside the sigma with k factorial over I factorial. And this should be starting to make some of you feel pretty happy, because hopefully you can see where we're getting to. This thing here is my Pascal's triangle coefficient, right? My binomial coefficient. So I've got e to the negative mu plus lambda over k factorial times this. But if you think now about what this is doing, this whole thing here, if we have a binomial expansion and we've got x plus y to the power of n, then this is just going to be n choose 0, x to the n, y to the 0, plus n c1. Right, we've done this loads of times. And we can write that in sigma notation as this. Right, so that's my binomial expansion. And that's exactly what we've got here. So we can replace all of that with mu plus lambda to the power of k. So we're working backwards from my binomial expansion. So there you go. And that's now equal to the probability of x plus y with mu plus lambda So actually that's written wrong. Let's fix that. So we can say that x plus y is distributed as Poisson with parameter lambda plus mu. So there you go. So that's the proof of the result. And what you need to do now is practice using it, doing some of the work in exercise 9b. So just one more time, what we've got is if we've got two separate Poisson distributions and they're independent random variables, then we can find the sum of them just by adding up their parameters. Thanks for watching. If anyone actually has watched this from this year's 13 MCA class, can you let me know, please, just so I know who is giving it a go.